Welcome back. Math 1910, Calc 1, Chapter 4, Section 4. Moving right along here through being able to figure out integrals. All right, we're going to cover the fundamental theorem of calculus in this section. All right, so we want to be able to evaluate definite integrals using the fundamental theorem of calculus. We're going to understand how there's a mean value theorem for integrals, okay, the average value function. All right, and then we're going to go over what the second fundamental theorem of calculus is and understand how to use net change. Okay, so for us, that's really going to be talking about total distance versus displacement. All right, we'll roll through some examples when we get through there. But the fundamental theorem of calculus for us, all right, this helps us solve the area problem. Remember, there's two major problems in calculus. There's the tangent line problem and there's the area problem. So this is the fundamental theorem of calculus, so it's theorem 4.9. States, if a function f is continuous on the closed interval from a to b, and capital F is an antiderivative of lowercase f on the interval a to b, then we can write the integral from a to b of f of x dx is the antiderivative of the function evaluated at b minus the antiderivative of the function evaluated at a. So this is called limits of integration. A and b are both constants in this scenario, and they are limits of integration. So they're going to be chunks of graphs that we are going to look at on the specific interval to find the area. Okay, so very basic, very fundamental. If we take a look here, some basic guidelines for using the fundamental theorem of calculus. One, make sure that we can calculate the antiderivative, or you have the tables or pieces from the front of the book that I gave you that show basic antiderivatives for specific functions. A lot of the trig functions, a lot of more complex functions and things like that. Basic ones you should be able to roll through and do in your head. Okay, make sure that you keep with your notation when you do the fundamental theorem of calculus. All right, so write out your integral and then take the antiderivative, and notice that we have the half of a bracket showing right there. That's showing that we are evaluating the antiderivative of b minus a, or f of b minus f of a. All right, where a is our lower limit, b is our upper limit, and we always do upper limit minus lower limit when we're evaluating the antiderivative. Okay, so if we take the example here, the integral from 1 to 3 of x cubed, okay, when we do that, we're going to rewrite that. The antiderivative of x cubed is x to the 4th over 4, and then we're going to do that little half bracket, okay, and show that we are evaluating x to the 4th over 4 from 1 to 3. So then we substitute in, all right, we're going to plug in 3 for x, so you're going to get 3 to the 4th over 4 minus, then we're going to substitute 1 in for x, 1 to the 4th over 4, so we're going to get 81 over 4 minus 1/4, which gives us 20. Okay, so very, very important there that we understand how to do that. That's where we're going to spend a lot of our problems in this chapter working on that. Also, another key element here, if we look at guideline number 3, all right, we don't have to worry about that constant of integration when we have limits. Okay, this is called a finite integral because we have the two limits. Since, remember, in section 1 where we had to do indefinite integrals where we didn't have limits, that's when we had to make sure we do the plus c. However, if you do the plus c here, it cancels out. All right, if we do the antiderivative of f evaluated at b plus c minus the antiderivative of f evaluated at a plus c, that minus will distribute to the plus c and make it a negative, and then we'll have a plus c and a minus c, and they cancel out anyways. So that's the good thing about when we have a finite integral, finite meaning that we will have a final answer, right, based on the limits of integration. Okay, so we don't have to worry about the plus c as long as we have limits on our integral. All right, so we're going to work through these three examples here. So let's work through the first one. We have the integral from 1 to 2 of x squared minus 3 dx. So first step, okay, antiderivative of x squared is x cubed over 3. Antiderivative of 3 is 3x. So we're going to have x cubed over 3 minus 3x evaluated from 1 to 2. So make sure that when you evaluate this, you put this into both parts, all right, into the x cubed over 3 and to the 3x piece when you do that. All right, and we always do the upper limit first. So you're going to substitute in 2 first. All right, so you're going to get 2 cubed over 3 minus 3 times 2. So you're going to get 8 over 3 minus 6. Then we do minus, and now we substitute in the 1. So you're going to get 1 cubed over 3 minus 3 times 1. So we're going to get 1/3 minus 3 when we do that. Okay, so as we simplify things down and stick with the algebra and simplify the fractions, we end up getting -2/3 for that integral. All right, next integral. We're going to go take the integral from 1 to 4, okay, of 3 times the square root of x dx. Now that 3 is a constant, we can pull it out in front of the integrand, all right, and then rewrite that x squared as, or the square root of x, sorry, as x to the 1/2, all right, so that we can easily take the antiderivative. And we've done this antiderivative multiple times, so I don't need to go through the steps on that one, but we get the 3 out in front, and the antiderivative is x to the 3/2 divided by 3/2, and we're going to evaluate that from 1 to 4. Evaluating the 4 first and then the 1, and then when we do that, okay, everything simplifies down to this, all right, and then our final value will be 14. All right, let's do C. The last example here, we're going to take the integral from 0 to 4 of secant squared of x dx. All right, what you need to do is be able to, the inside handout, inside of the book handouts that I gave you, okay, if you don't remember your trig functions well, we'll show you the basic integrals and derivatives for the trig functions. So we should know that the integral for secant squared x dx is tangent x, right? The antiderivative of secant squared x dx is tangent x. So we're going to take tangent x and evaluate tangent x at pi over 4 and 0. So we should know that tangent of pi over 4 is equal to 1, and we should know that tangent of 0 is equal to 0 when we go through this. All right, so 1 minus 0 is 1. All right, let's take a look at how we apply a mean value theorem for integrals. Remember, we had a mean value theorem for derivatives. We also have a mean value theorem for integrals. So Theorem 4.10 says, if f is continuous on the closed interval a to b, then there exists a number c in the closed interval a to b such that the integrand, all right, of a to b of f of x dx is equal to f of c times b minus a. Okay, so that's really just using our mean value theorem. If we are asked to calculate something with the average value, okay, so the definition of the average value theorem, right, or it's not a theorem, but the definition of average value is if f is integrable on the closed integral or interval from a to b, the average value of f on this interval is going to be 1 over b minus a times the integral from a to b of f of x dx. So really all we're doing here is we are adding 1 over b minus a, all right, which is our limits of integration, to find the average value over those specific limits when we do the calculation. All right, so let's do an example here. We want to find the average value of f of x if f of x equals 3x squared minus 2x on the closed interval from 1 to 4. All right, so 1 is our lower limit, 4 is our upper limit, and we want to find the average value. So remembering that that's from the previous slide, that's 1 over b minus a times the integral from a to b of f of x dx, we get 1 divided by 4 minus 1 times the integral of 1 to 4 of 3x squared minus 2x dx. Okay, that 1 over 4 becomes, or 1 over 4 minus 1 becomes a third, and we're going to keep that out in front of the integram, and we can multiply through by a third at the end. So then we just really need to focus on the integrand and taking the antiderivatives. So when we do that, we're going to have 1/3 times the antiderivative of 3x squared is x cubed, and the antiderivative of 2x is x squared. So we're going to have 1/3 times the quantity of x cubed minus x squared evaluated from 1 to 4. So we're going to substitute in the 4 first because it's the upper limit, and then substitute in the 1 because it's the lower limit. So we're going to get 1/3 times 4 cubed, which is 64, minus 4 squared, which is 16. Okay, then there's minus, we got to do 1 cubed minus 1 squared. So that gives us a 1 minus 1. That piece goes to 0. Okay, so then we are left with 48 over 3, and 48 over 3 reduces down to 16. So here's where our average value theorem comes into play. All right, so the average value for f of x equals 3x squared minus 2x is 16. Okay, let's take a look real quick at the second fundamental theorem of calculus. Okay, we saw that really the big difference between the second fundamental theorem and the fundamental theorem is the limits of integration. So with the fundamental theorem of calculus, the limits of integration are constant values. All right, we're going to go from 1 to 4 like we did in the last example, or 2 to 6. With the second fundamental theorem of calculus, it allows us to do an integral that has a variable as a limit of integration. Okay, so you're going to have x as a limit of integration when you do this. So when we write this out, we have the integrand. All right, so we have the integral from a to b of f of x dx. That's what we've done on the left, right? A definite integral. We had limits, and the last example it was 1 to 4. If we have the one on the right-hand side, notice the only difference is instead of going a to b, we're going a to x, where x is being used as a variable now. X is not a constant value there, so x can be, multiple values that we're going to figure out here soon. So when we do that, all right, notice the function now is f of t, so we're doing everything with respect to t when we do this. Okay, so all right, moving forward here, we want to evaluate the function here, 0 to x of cosine of t dt. Notice x is our variable of integration now, instead of having a constant limit there. So 0 is one of the limits, x is the other limit, but now it's a variable. So if we wanted to evaluate this at x equals 0, pi over 6, pi over 4, pi over 3, and pi over 2, okay, we're going to run into a lot more work. We got to redo that integral multiple times. Whereas if we do the integral first with just x and then apply it at the values we want to, okay? So instead, we're going to use x as our limit. So we're going to we have 0 to x of cosine of t dt. The antiderivative of cosine of t is sine of t, and we're going to evaluate sine of t from 0 to x. So that really just yields sine of x minus sine of 0. So we're going to keep sine of x as sine of x, obviously, and we're going to put in a bunch of different values for it. And then we have sine of 0. Sine of 0 is 0. All right, so really when we just do this integral here, we're getting sine of x. And then we can evaluate sine of x at 0, pi over 6, pi over 4, pi over 3, and pi over 2, because we can substitute in now. So it's really just going to be those values when we do this. Okay, so if we graph them and look at the different results, right, obviously the first one is 0. There's no area under the curve there. Then if we look at f of pi over 6, we end up getting 1/2. If we look at f of pi over 4, we get square root of 2 over 2. If we do f of pi over 3, we get square root of 3 over 2. If we do f of pi over 2, we get 1. All right, the entire area under the curve there. All right, so that's really how that plays for us. And we have a special thing that we call these, okay? This is called the accumulation function. And we use it in multiple, applications of integration here. But we're accumulating, right? I'm going to step back a slide. Well, how are we accumulating? Well, as we chunk forward and choose different sign values, so that's the accumulation function, right? As we just go along and we get little chunks, you can see that we get more and more area under the curve as we go through that. So that's really when we're going to use an accumulation function, because we have some sort of variable as our limit of integration. All right, so let's look at the official, Theorem 4.11 or Theorem 4.11, the second fundamental theorem of calculus. Okay, another way that we can take a look at this is if f is continuous on an open interval I containing a, then for every x in the interval. Now, look at what's going on here that's different. We're taking the derivative of the integrand. So d dx means we're going to take the derivative of the integral from a to x of f of t dt. And it's going to give us back f of x. But you got to be careful here, right? We have, for this to work, right, we have to have one of the limits as the variable x, and our function has to be in terms of t or some other variable other than x when we do this. Okay? The derivative and the integrand, cancel each other out, kind of like a square and a square root scenario play out there. Okay? So that's how that works. So let's look at an example here of the second fundamental theorem of calculus. We want to take the derivative of the integral from 0 to x of the square root of t squared plus 1 dt. Alright, so we know if we do all the antiderivative and everything, where we're going to end up being, that it's really just going to be that x that kind of goes in here. Okay, we know that the square root of t squared plus 1 is continuous on the entire real interval line. So we can say the derivative with respect to x of the integrand from 0 to x of the square root of t squared plus 1 dt yields just x square root of x squared plus 1. So simple substitution here as we're going through using the second fundamental theorem of calculus. Alright, let's talk about net change now. Alright, so if we want to talk about net change, we're really just running through the integral there. Notice there's really nothing special on the first one there. Alright, if we just do the integral from a to b of f of x dx, we're evaluating the antiderivative at b minus the antiderivative of a. Okay, so that's the fundamental theorem of calculus. Alright, so let's go ahead and do a net change calculation here. Alright, if we look at Theorem 4.12, the definite integral of the rate of change of the quantity f prime of the antiderivative gives the total change or net change in that quantity on the interval from a to b. Okay, so if we want to take, the derivative of the antiderivative, okay, to calculate the net change, it just ends up being f of b minus f of a. Okay, so let's do the example. We have a chemical that flows into a storage tank at a rate of 180 plus 3t liters per minute. Alright, and time is between 0 and 60. Find the amount of chemical that flows into the tank during the first 20 minutes. Okay, so that's the important part. We're just doing the first 20 minutes when we do this. Okay, so we can designate that C of t is going to be the amount of chemical in the tank, and our C prime of t, okay, is the rate at which the chemical flows into the tank. Alright, so we're going to integrate this from 0 to 20 because we're talking about the first 20 minutes, and then C prime of t is going to be our given equation of 180 plus 3t. So we're going to do the integral from 0 to 20 of 180 plus 3t dt. Alright, and then we take the antiderivative, so we're going to take 180t plus 3 halves t squared evaluated from 0 to 20. Alright, this is no different than what we've been doing. It's just a different, a finite integral. Okay? And then we evaluate it at 20, substitute in our values, and we end up with 4,200. Okay? So that's the amount that flows into the tank during the first 20 minutes is 4,200 liters. Okay, as we do that. Alright, so really just, different ways of illustrating net change and things like that, alright, is using velocity. The other way we describe net change, alright, deals with displacement of a particle, alright, and we got to understand the difference between displacement and total distance. Alright, so best example, you go to the grocery store and then you return home. Your displacement, is 0. But if you drove 5 miles there and 5 miles back, the total distance you traveled was 10. So the displacement is, how far away you are from when you started. Okay? Total distance is how far you actually went in total, whether it was on the way there or the return path, things like that. Okay, so really important, as we discuss this and as we talk about particles, moving from left to right and those sort of things, we want to be able to calculate the total distance traveled. Okay, so we have to understand the difference, like I just said, between displacement and total distance. So displacement, okay, is where we just do our normal integral. Okay, just our normal fundamental theorem of calculus. Okay, now when we talk about total distance, we have to make sure we do the absolute value. Let's take a look at the graph down here. Okay, we notice that area 1 is above the t-axis, area 2 is below the t-axis, and area 3 is above the t-axis. So when we do total displacement, we can do the total integral, because when we integrate there, it's going to account for the area that's above the t-axis, which is area 1 and area 3, and it's going to account for the area below the t-axis, which is area 2. But to get the total distance, all right, the reason you can't use the whole integral is because area 1 and area 3 are positive and area 2 is negative, all right? It would take away from the total distance. So you have to make area 2 positive. Okay, so the total distance traveled has to be the absolute value of everything. So that's why we have to say we got to make area 1 plus area 2 plus area 3, but we have to do the opposite of area 2 to make sure that it's positive. Alright, so let's do an example here. We have a moving particle. Its velocity is represented by t cubed plus 29t minus 20. Or I'm sorry, t cubed minus 10t squared plus 29t minus 20. Alright, we want to find the displacement from 1 to 5 and the total distance traveled when the seconds are 1 to 5 when we do that. Okay, so we have to make sure that we pay attention. If we know we want to find displacement, alright, we're just going to integrate, use the fundamental theorem of calculus. So we're going to do the integral. Alright, we're going to find the antiderivative of everything and then evaluate it from 1 to 5. So make sure that we're accurately finding the antiderivative, evaluating from 1 to 5, simplifying everything down, and we end up getting, alright, the final solution of 32 over 3. That's the displacement. That's how far we are from where we started. It might go, left, right, a whole bunch of times, but based on where we started, it's moved 32 over 3 feet to the right. How do we know it's to the right? Because it's positive. If we move to the left, it would be negative. Alright, so next let's calculate the total distance traveled. Here's where you got to really pay attention. Okay, we can see if you graph this or you factor it, alright, it factors into t minus 1 times t minus 4 times t minus 5. Those are the zeros. Very important. Notice from 1 to 4, our v of t is positive. Okay, from 4 to 5, it's negative, but we want to find total distance traveled. So we have to do the opposite of the integral from 4 to 5 to make sure that our value comes out positive there. Because if we did the integral of this function from just 4 to 5, we would get a negative value. So we have to do the opposite when we set this up. So the total distance traveled from 1 to 4 of v of t, that's the positive piece, and then we have to do the opposite from 4 to 5 of v of t because it's negative area there. I'm stepping back and looking at the graph, all right? 1 to 4, it's positive area, 4 to 5, it's negative area. So we've got to make sure that we account for that. So that's why we're going to subtract that second integral. Okay, we'll subtract that second integral so that the sign actually comes out positive because that area from 4 to 5 is going to be negative. So when we do minus a negative, it becomes positive. So just know that that's how you're going to work it out. The antiderivative is the same for both, just how we evaluate it's going to be slightly different. Okay, so same antiderivative. Now we evaluate it at 2 different locations. So we're going to end up with 45 over 4 minus negative 7/12. Now it becomes positive, and we ended up traveling a total distance of 71 over 6 feet. What you need to understand is that displacement will always be less than or potentially equal to the total distance. Displacement will never be greater than the total distance. Okay, so your total distance always needs to be positive and it always needs to be the larger one. Displacement will always be the smaller one. It may equal total distance, like if you drive to the grocery store and just stay there. Alright, your displacement, if you drove 5 miles is 5, and if you stay there, total distance traveled is 5. So that would be one scenario where that would happen. Alright guys, well that's the end of this lecture. If you have any questions, feel free to email me. Let me know if we got a Zoom meet, team meet, or anything like that. Else, I will see you in class. Have a great day.